let's have a go at doing one going the other way. So in this case we've got a curve which is in, no, it's the same way as before, isn't it? This is in polar to Cartesian, and this is polar to Cartesian. This one looked really ugly in polar form and came out quite nicely in Cartesian form. This one looks quite nice in Cartesian form, but I suspect that you don't actually know what that curve looks like. So we'll put it into Cartesian form and see if you can recognise it. Now, there's a bit of a nasty trick in this one, in that, again, we could write r as the square root of x squared plus y squared, and sine theta as the sine of tan inverse. But if we just multiply both sides by r, we get this side looks nice and easy now, and r squared is nice because that's x squared plus y squared. So we just end up with x squared plus y squared equals y. Okay, which is simple enough. But in terms of what it actually looks like, let's try and get into a form that you might recognise. So x squared plus y squared minus y equals 0. And if we complete the square on that, we get x squared plus y minus a half squared. So that's y squared minus 2 lots of half of y, which is minus y, plus a quarter. So I've added an extra quarter. So I better add a quarter onto that side. Okay, and that hopefully you'll recognise as being a circle centred on 0, 1/2. There's nothing within that half with the y, and with a radius of the square root of a quarter, so a radius of a half. Okay, so that's a very simple structure. Much more complicated, but this is one we recognise because we've dealt with Cartesian coordinates in the past. But it's much simpler to describe the circle as a polar form than it is in Cartesian form. So once again, let's have a go at drawing a graph of that polar form just to convince you it's actually right.